you so much, Jane, and thanks to all for inviting me. And it's such a tremendous pleasure and honor to be with you today. Please let me know if I'm not audible enough in the room or if you're unable to see the slides that I'm about to show you. I'm very sorry I can't be there in person, but I have to teach a class full of eager students this afternoon, and it just wasn't possible for me at the moment. I did have the honor of being there in July for the meeting that Jane just talked about, and I must say it was extremely spiritual and wonderful to be in the Vatican. So what I'm going to talk about today is directly related to what Jane was just discussing. If you can't, you should now be seeing my slides. If that's not the case, someone should please let me know. It's basically the question of variability. What's certainly on all of our minds is the tremendous suffering going on around the world right now, really, around climate and weather, and understanding how much of that is the forced signal, how much of that is due to human activity versus the internal variability of the climate system. And I'm going to try to summarize for you some of the advances that have happened in the last 10 years around the way climate science attacks that problem, mainly for precipitation and temperature, but also a little bit for runoff and related things, like including hopefully ecosystems, if I have time. Well, we all know that the world has warmed. This has been the warmest decade since at least the late 1800s. It's about 1 degree Celsius warmer than it was in 1880. And as we know, the Paris Agreement goal is to keep global warming well below 2 degrees and pursue best efforts not to exceed 1.5 degrees. I always find it illuminating to look at the warmest individual years and sort of run your eye down them and ask yourself how far back you have to go before you find one when you weren't alive. And I think for just about everybody in the room, we go off the end of the list, which means that we have been living in the warmest period in the instrumental record. Even for young people, they've been living in at least the top 10 or top 15. But when we think about things, we don't often think about the global average. From science point of view, we do, but individual people often don't. They want to know about their own backyard right now, and they want to understand the difference between weather and climate. We all know about weather. We see it in weather forecasts, the way that fronts push air from one region to another. This example of a winter cold front coming down out of Canada and making the northern states in the US cold is typical. But it's important to notice how when the northern states get cold, the far western states get warm. So if you average across that, you typically don't get much change. And that's really the difference between weather and climate. But what does it mean for how people understand climate change? If we look at local and global trends for just the month of January, we see patterns that look like this, with the biggest warming being at the higher latitudes in the northern hemisphere. And it sort of attracts our eye to the idea that that must be where the most climate change is happening, or definitely must be happening. That isn't true, as I'm going to show you. And the reason is because of variability. When you look at the ups and downs in January temperatures, at, for example, a spot in the middle of Western Canada, you do see a trend, but it's part of a panoply of years that go up and down, and it's difficult to be certain that that trend is statistically significant. Same sort of thing, not quite as much amplitude, happens in Australia. Same kind of thing when we look near Paris, for example, or near Denver. Although one of the things that I should point out when you look at Denver is the way that the coldest Januaries are getting warmer. And that affects ecosystems and things like the pine bark beetle, which is killing off Western forests. So even though there's a lot of variability, the trend in that variability can sometimes be important. if we go ahead and average across the whole globe, now we don't have to be a particularly great statistician to be able to see that indeed there is a clear and significant trend. So this is why people have trouble. Avoiding noisy signals is sort of natural. There's been a great deal of scientific work, and I'm just crediting some of the people who really, I think, laid down the ideas initially, something like 10 to 20 years ago, around this problem. Basically, one way to look at it quantitatively, which has become widespread now, is to run what we call climate model ensembles. So instead of taking a model and just doing one numerical simulation, say of the period of 2000 to 2060, you want to take a look at how variable the prediction for 2060 is. How do you do that? You can do it remarkably easily. You started out with identical land, ocean, and sea ice conditions, but you start from a slightly different atmosphere. And the way you do that is pick, say, if you're going to do 40 of them, pick different days in the 60 days between December and January of the year 2000 in the base run that you start from. And that's actually enough to produce remarkably different climate realizations. And in the real world, we only get one realization. So that should give us a sense of how much variability is superimposed on anthropogenic effects. So the reason for that is fundamentally just the random nature of the chaos in the weather system. So here's an example of what we find when we do that. If we look at winter season temperature changes, December, January, February, the average over North America looks like this out of our 40 runs. The warmest one is really hot, and the coolest one, for say parts of Western North America, is actually a little cooler, and not nearly as much warming in other places. So it's very instructive, we found, to pick out just a couple of points. We're going to pick Seattle, Phoenix, and Mazatlan, and take a look at the temperature changes over that winter season, the ups and downs. And what you can see is that for Seattle, it's not nearly as obvious that the kind of extreme heat that they actually did suffer this summer and have suffered in previous summers, it's probably significant, but it doesn't need to be. So you have to be careful. If you look at the United States as a whole, slight warming, but not necessarily the type of warming that we've had, although the type of warming that we've had is certainly one possible realization. For the whole globe, indeed, everybody warmed. But look at what happens, say, in Mazatlan and Phoenix. The lower latitudes are the ones where you see a more obvious change emerging already. And you can actually visually see why that is. Take a look at these histograms on the right-hand side here. And you can see it even here visually. The variability from year to year in Mazatlan is a lot less than it is in, say, Seattle. And so this trend that has emerged is significant relative to that variability, both interannually and on the decadal scale. So, clearly then the people that are going to be suffering the most, and I'll show you more about this in a couple of seconds, and the ecosystems that will suffer the most are the low latitude places. They don't necessarily have the largest warming, but they have the largest change relative to variability, which means that the measures for adaptation and resilience are not needed there normally in the same way they are at higher latitudes. And then that's really a big part of the problem. So why is this happening? Well, it's basically because of the effects of circulation, like that cold front that I showed you before. The same patterns that dominate weather actually also are important for climate. So the years in which you have a cold winter are the ones where you systematically get more often those cold fronts coming out of say, Canada for this region. And when you get southerly flow from the south to the north, that's when you're going to get the hottest summers. And these low latitudes are simply outside the reach of these circulation changes. There's also linkages on multi-decadal timescales to slow changes in the ocean, and I'll mention that in a second. I guess here it is. So if you're wondering, well, what about slow processes that might take, say, 10 years, 20 years, 50 years to emerge? One way that you can look at that is to compare the variability seen, the standard deviation of local trends over, say, 56 years in December, January, February. This is the future projections. But if we take a 1,000-year control run and break it up into 178 chunks of 56 years, we get very much the same pattern. Incredible, actually. And that's what tells you that the places where you can see a significant trend are largely these tropical areas, which are stippled here. Another way that you can do it, that maybe you don't want to just trust one model, of course, you can look at the patterns that you get in one particular model, CCSM3 versus ECM, which is the German model, actually. And you can see the similarities in the ensemble mean trends between the two models are remarkable. In both winter and summer, everybody's warming to some extent, but the standard deviations are also large, especially at the higher latitudes. So the places with significant trends in both models are going to be at the lower latitudes. So what this really is what some people like to call the butterfly effect, that you have very tiny differences in the starting conditions that actually lead to very different realizations of climate. And that's what's happening in the real world too. But it happens in every one of these 40 members. So as I mentioned, it's really the low latitudes that are on the front lines of global warming, if you will. You have places where you have different summers already, say in parts of Africa here, where the variability past variability is clearly less than the noise. And you have places where different summers are coming, but they're not here yet, like parts of Russia. Precipitation is a more difficult problem. You get more areas of disagreement between models and between members of these ensemble runs. So between the 40 members, there's more variability. You can again look at two different models and take a look at the drying. And while there's some drying in the Southwest United States, for example, that's seen in both models, there's also interesting differences between the two models and between the trends and the standard deviations. So for example, although both models seem to get this wetting trend, say in parts of Alaska and Western Canada, that's also where the standard deviation is very large. So you can't really be sure that that's real. Now, in the case of a heavy rainfall, we do know that heavy rain is happening more often than light rain on essentially a global scale. So that raises a lot of issues, not least of which is the terrible situation in Pakistan right now. Another thing that you can look at is runoff, where the runoff of rivers depends not only on how much rain falls, but also on temperature, which drives evaporation. And so if you look at all these different climate models, you see differences between them, but you also see that virtually all of them have some similarities. I'll just point out, for example, Southern Africa, the tremendous drying that almost all the models give. And again, Western North America, Spain tends to dry in essentially all the models. And we're definitely seeing that now. What that means is that you're going to need more irrigation water if you want to grow something like, say, wheat. And by 2050, you're going to have some parts of the world, we believe, where you're going to need 30% more irrigation water to grow wheat. And you may not have it. And that's a huge problem. Again, Parts of Africa look to be particularly vulnerable, but also the Mediterranean and parts of North America. So I'm almost done now. I just want to mention that this has implications for many aspects of the ecosystems, not just human beings. I really love this classic paper on the issue of how to think about this. If you look at what they call the fitness of, say, insects, the tropical insects tend to be able to function, to move, and to reproduce in a fairly narrow range of temperature, whereas higher latitude insects are more adapted to variability, as you would expect based on what I just showed you. So it's really the tropical insects, that and tropical forests, tropical everything, if you will, that are going to be the most vulnerable. So my message really is, indeed, the world is warming on average. Averaging over space and time, though, doesn't overcome the fundamentals of predictability. There could be other forcing mechanisms. I just want to mention that what's happening with the monsoon in Southeast Asia may also have to do with aerosols. So it's maybe not just CO2. The largest local warming doesn't necessarily give you the places with the biggest signals of noise. Unfortunately, it's the people contributing the least to warming, having the least emission, that happen to be on the front lines of this problem. When you look at, when people talk about ensemble modeling, I hope I've helped you to understand how useful that framework can be. And obviously there's widespread impacts of this way of thinking on everything from flooding to extinction to wildfires, coral reef vulnerability, and much more. So thank you very much for your attention, and that's it.
Thank you indeed, Susan. Really nice summary of lots of very hard work by a lot of people. Any questions for Susan? Yes.
Fantastic presentation, really, really illuminating. Is my view very negative? Looks like everybody is giving up on mitigation and just moving towards adaptation, in a sense that there's almost, I'm throwing the towel, there's nothing I can do about it. The Paris Accord is down the drain, or how do I see that?
Well, I mean, that's another talk altogether. But it is obviously the question that's on all of our minds. I guess all I want to say very briefly about that is we can't let that happen. I mean, we cannot let that happen. If that happens, the devastation for the world is enormous. I mean, we're only seeing the tip of the iceberg of how terrible this problem will become if we give up on mitigation. But I guess I think there's a reason to be optimistic, and that reason is the fact that methods to mitigate have gotten incredibly cheaper in the last 10 years than they used to be. So the cost now of solar and wind power is lower than the cost of, say, coal and even gas in most of the world. So it's not a question anymore of this is going to be tremendously expensive, we can't afford it, blah, blah, blah. I mean, that is simply no longer true. And I think the Europeans, to be honest, deserve a tremendous amount of credit for pushing that technology forward through the Kyoto Protocol and also the type of policies that they've had. In the US, we've also put a lot of emphasis, at least on research. And all those things have made solar and wind cheaper, also batteries. Everything is coming down in cost at a phenomenal rate of speed. Even in Saudi Arabia, solar is now cheaper than other forms of power. That's fantastic. So you will see huge changes happening, purely driven by economics. We have to push those along as fast as possible. That, however, is the reason why I'm not giving up on the Paris Agreement.
So I would note that the IPCC, the most recent IPCC, addressed this directly and made the point of saying that every degree, every fraction of a degree of warming matters. And so that underscores the urgency of reducing emissions as rapidly as possible while also preparing for the adaptation. So it's absolutely not a matter of giving up. It actually is the matter of doing more, both reducing emissions and adapting. Mohammed, the last question, and then we'll move on.
It's actually just a comment on that, what you have just said. I think for a long time, adaptation has not been receiving that much attention. It's only very recently at COP26 that more attention has been given to it. And the poor countries are really suffering a lot from climate change, and they haven't contributed that much to the emissions. So for them, adaptation is really the problem, and to increase adaptation is what they really want, and they want a lot of support and help from the international community. But the areas like the renewable energy, the one that you just mentioned, I think is an area that can serve both adaptation and mitigation. And this is where we really should try to put a lot of effort and finance.